All right. I was wondering if you all could help me out for a little bit. My name is Scott McAllister. I work for a company called Loft Labs, but I come from Seattle, Washington, and I need to prove to my bosses that I didn't come to New York City just to come to one of the biggest, greatest cities in the world. So if you could all smile and wave. Awesome. Thank you so much. We'll put that away. So if you're here for the next 25 minutes, I'm going to be here to ask you questions that will hopefully get you to ask yourself questions. Ask yourself questions about how you're running things in your organizations and with your infrastructure, and wondering why you're doing it. And I'm going to do that by talking a little bit about history, a little bit about the history of computing. I'm going to go back in time a little bit. I'm going to go back way back in time. Yeah. Even back before computers, this is a line shaft factory. Line shaft factories were essentially a mechanism that had a central power supply, so like a steam engine, that had shafts where the steam would fly through. It would operate these pulleys. The pulleys would operate the straps, which would go down to the individual machines. It was essentially automation back in the 1900s. And it worked really well, except it took a lot of power to get that power to go up through the shafts and down to and operate the pulleys. And so it worked, but it was expensive. They had to build factories in multiple stories so that they could actually use the steam engine, the steam power to go up through the shafts to actually push the pulleys. And then if you wanted your little machine to get onto the factory operating thing, those straps, thank you, were turning all the time. So if I wanted to get my machine in front of me to get onto the shaft processing power, I would take it and put it onto the pulley with my own hands. I'm sure that also cost some fingers and hands and things. And so this worked great, but then we got electricity, and we thought, hey, we have electricity. This is a new power source. We'll just take what we have, which is this big steam-powered engine, and we're going to stick in a big electric engine. It was called an electric dynamo. They lifted the steam-powered engine and shifted in an electric dynamo. Sound familiar? Maybe a little bit. It took decades for us as humans to really embrace the fact that we had a new way of providing power to our factories. It wasn't until 1920s that we decided, wait. I could take this power, take it to my different machines, have it be separated to the different workstations, and then I can operate my factories in a little bit more efficient manner. I can build one-story buildings rather than multiple-story buildings. I can have buildings that are more configurable. And so it took decades for us to really embrace the fact that this new technology could be used in a different way if we just thought about it differently. Now we're here at a computer conference talking about computing and software. This, my friends, is an IBM 360 mainframe. And other than being the machine that actually my dad programmed on back in high school, he told me when I was showing him these pictures, he would do the punch card programming into one of these. This was also one of the first machines that allowed virtualization. Not a full-blown hypervisor, but it actually provided the way to develop those hypervisors. On it, it allowed the development of what's called CP67, which was one of the first hypervisors that ran on, I have to get this right, VM370, which was, again, actually ran on the System 370 IBM mainframe. With that virtualization, that term hypervisor, IBM coined this term to describe hardware virtualization. Our hypervisor is that virtualization layer that allows for virtual machines to run on top of it. We can run lots of virtual operating systems, on one set of hardware. It abstracted out our CPU, our memory, and our storage to make it possible. Now, hypervisors essentially evolved into two different types. First, we have the type that's called bare metal, which is kind of getting a little confusing because, we have the whole concept of bare metal Kubernetes. But this is actually virtualization running on bare metal because that hypervisor is running directly on the hardware. No underlying operating system. That hypervisor, that type 1 hypervisor, you can put the VMs right on top of the hypervisor running on the hardware. Then we have that second type of hypervisor, which actually needs an operating system. This is the kind that has products like Oracle's VirtualBox, VMware's Workstation, VMware Server. The first type, things more like Hyper-V from Microsoft, right? So along with virtualization, we also evolved with our software development. We went from running monolithic applications, large code bases that were clunky and hard to maintain, and we'd start separating things out into services. Those services have specific functionality in each of the services, and we thought, yep, this is the way we want to do things because we can scale things. It's easier to find bugs when you're looking at smaller bits of code. And so we continue on with the evolution of our technology. And you might think that containers are a relatively recent innovation, but the roots actually trace back to the 1970s. In Unix systems, there were tools like chroot, which allowed to isolate application code. And these early implementations of this type of technology, the containerized technology, provided basic isolation but lacked portability. So it limited their broader adoption. So over time, advancements like Linux namespaces and C groups enhanced container capabilities, setting the stage for modern containerization, which came in 2013 with Docker's innovation, pivotal moment in the containerization of our applications. So with containers, very similar, right? Very similar idea as virtual machines, yet not. The reason why we have containers is so we have a much more versatile, much more streamlined piece of software that's running our applications. It's just having our application code and our dependencies and not the full-blown operating system. And then with those containers, we're able to take into our services, apply those to our services, and now we can say, hey, great, I can package up my service, I can start versioning it, I can replicate it, I can scale this thing, all using inside of containers. So containers help provide even a better layer of definition around our services. But as you see on our applications, as our services expand and our containers expand, we have a lot of containers to wrangle, and so of course, came the evolution of Kubernetes, coming out of Google based on their internal systems they used for managing their large number of containers. Kubernetes allowed us to automate, to scale, to replicate things so that we could have a way to organize our containerized applications. When we found, or when we, I should say discovered, when this new technology of running our applications in containers came about, we thought, great, I'm already running my applications on a virtualized system. I'm saying, okay, on my virtual machine, I have my operating system, I'm gonna run my container runtime and then put Kubernetes in there, and now I have Kubernetes running on my system that was already running my virtual machine. So I'm virtualizing a system that's gonna take containers, and which are kind of virtualization, and run that too. Kind of sounds familiar, doesn't it? Which leads to the question, are you VMweary? Are you using virtual machines based out of the fact of habit, or do you have actual technical need for running virtual machines? The current state of software infrastructure seems to be at a similar crossroads as when we were talking about the factory, the line shaft factory that had the new electric engines that we were applying to our factories and realizing, wait, we could do this differently. So are we trying to solve modern platform problems with legacy thinking? So to answer that, let's step back and look at how we got to this spot with our applications, with our own infrastructures and our own decisions that we made. We start by looking at why, how it started with running Kubernetes in a virtualized environment. First, it was familiar. We already knew the stack. We already knew how to deploy onto a virtual machine because that's what we've been doing for decades. So we thought, okay, we'll just keep doing that. Also, virtual machines are scalable. They make it possible to, relatively quickly scale up a new machine with a click of a button, right? But then also, it provided tenant isolation. This was key in the sense of that way now I can run our your machines in multiple environments. You can have them for multiple customers, multiple users, multiple employees, multiple developers, multiple teams, all having similar infrastructure, but isolated to have different tenants running inside your clusters. So how's it going? Well, it's expensive. If you look at your virtual machines today, not even remotely talking about the recent price hikes from certain virtual machine makers, but also the pricing model for virtual machines. A virtual machine is constantly running. You're paying for it to be constantly running. Your workloads inside of your Kubernetes clusters are not constantly running. They're probably either they're spiking with traffic that comes in or with workloads from your developers as they're working during the day and then maybe not working at night. I recently heard a key point or a bit of wisdom. If you think about your developers, how often are they actually working? Yes, probably, 8 hours, yes, but here in New York, maybe 10 hours every day. But then all of those hours while they're sleeping, their infrastructure is still running. You're still paying for that VM, for that infrastructure, for their development environment. Why are we doing that? Also, a lot of virtual machines are underutilized. We have virtual machines for every situation that we have, that we're thinking of, whether it's internal development platforms or for each customer that we have. But you have a big, beefy virtual machine that could be running small clusters. As we've talked to folks who are running their applications, we've found that this is quite common, where people have lots of virtual machines that are running small clusters that are really underutilized. And then also you have a redundant complexity. Redundancy is great in storage, right? When you're trying to store data, you want to be redundant where you're going to store the thing, but when your application configuration and your infrastructure and how everything's layered up to how to running your application, not something you're really is that something really providing you value? And then virtualized hypervisor environments have a price. They have a price and performance overhead. You have to run that whole virtual machine, that whole operating system that's running your application or running your particular cluster. Up to 30%, has been said, that is all just going into making sure that machine's running before it's actually running your application. That's processing that could be going into running your applications rather than just your cluster. So if any of this resonates with you, you might be thinking, okay, well, what now? The suggestion that I propose is to consider the performance enhancements and the cost savings of running Kubernetes on bare metal. There is a company down in Australia. They're called Aussie Broadband. They are an internet service provider that provides internet and communications to folks down in Australia. And they were running in a virtualized environment, and they wanted to get off of their VMs and to run on bare metal. In doing that, they were able to eliminate 195 VMs in their environment, remove over 1,000 CPU cores and over 1 terabyte of memory. And more importantly, as we learned in the keynotes this morning, right? Kubernetes runs business. The business of reducing your costs so you can maximize your profits. They were able to reduce that VMware cost to 0. But they had a problem because they needed a way. One of the reasons why they were running in VMs is because they need to have multiple tenants running in their clusters. They have multiple people using their resources and using their containers. So they thought, okay, we need to investigate how are we going to go bare metal but still provide this multi-tenant environment. And the folks over at LearnK provided this great spectrum. I love it because it shows all the different options, probably not even all of them, but many of the different options that are available in the industry today. On the far right, you have namespaces, which is like the bare minimum way of separating things out. We're basically, we put a name tag on things and say, well, this is mine, these are my pods, and those are your pods, and yeah, those are namespaces, and that's nice. But what happens when we start installing CRDs, and I say, well, I want one version of Nginx, and you want a different version of Nginx. And those are installed on the cluster level. Namespaces aren't really going to help you in that situation. Then we can go to the whole opposite end of the spectrum on the far right and say, well, then we can give unique clusters to each tenant. Yeah, we could do that too. But in many situations, especially in cloud environments where you're paying per cluster, that can get pricey too. And think about the maintenance of trying to manage all of those different clusters. There in the middle is something called vCluster. Now, vCluster is a way to provide multi-tenancy inside of a Kubernetes cluster by putting a Kubernetes cluster inside of a pod of an existing cluster. Now get this. So you can install vCluster and create a vCluster that's running inside of a cluster running on your machine, on your server. And now you have an environment that is basically able to take resources from that host cluster and say, I'm going to use the cert manager from here and the ingress controller, and so that I can have those into my vCluster. But then I'm going to use my own versions of other things that I have running inside of my application, or inside of my infrastructure. Then I have another tenant that can say, I can run my own set of CRDs, and I can have my own isolation inside of my cluster, so I can have my own vCluster. So we have two different tenants, tenant A, tenant B, and they can share some things that are synced back with the host cluster, but then also have their own unique environments as well. This comes in at a time when most environments, or many environments, look a lot like this, where we have a collection of physical servers that have VMs running on top of them, but those VMs aren't highly utilized. And in that situation, you're thinking, well, I'm paying a lot of money for those VMs. That's a lot of resources. So we need to come up with a better idea. So you could have an idea where you have a large cluster that's going across your physical servers, and then you have virtual clusters inside that cluster that are much more utilized. And then those virtual clusters can have logic in them that say, you know what, we're going to watch the traffic. And if the traffic in this virtual cluster goes down, we're going to spin down. We're going to make it possible so that you can save money and resources if you're not actually using those resources. So Aussie Broadband, when they adopted vCluster, they were able to not only provide a bare metal situation or bare metal Kubernetes to their environment, but they were also able to provide multi-tenancy to their shareholders, to their development teams, essentially. In that, they were able to provide faster cluster provisioning. vClusters spin up a lot faster as they're much more lightweight than a host cluster that's running on your machines. But also, with that, they're able to have faster deployments, save a bit of money, but then also save time. Development time, that's money. If you think how much you pay your developers, how much time you have when they're deploying things, when running things, and setting things up, or they're waiting for something to compile, or waiting for an environment to spin up or spin down, definitely time and money there. So multi-tenancy is not only just for current workloads and current things, or at least operations that we've done up until now, but current things, I should say, because it is current. AI is current. Working with GPUs is now and in the future. We need to be able to think about how we're going to utilize these very expensive pieces of hardware. If you're ever in the market of trying to get a GPU or get space on a GPU, not very cheap. So you want to utilize those pieces of hardware. You want to utilize those nodes. Those DGX nodes that through Nginx, sorry, too many words in my head, NVIDIA, provide that type of processing that you might need to work with your AI models. But with those, we have libraries, we have tools like RunAI, Kubeflow, Volcano, and others that provide that type of scheduling that you would need to utilize those nodes. So with those different tools, those different libraries that we have, you can have a virtual cluster. You have vCluster tenants that are utilizing these libraries. That way you can have multi-tenancy inside of your host cluster, inside of the cluster that's using the different libraries that are running AI for your applications, but then also provide it in a way that it's the Kubernetes way of doing it. That way it's not having virtual machines that can't cut up a GPU processing, but you can handle that through these different tools and then using virtual cluster or vCluster. So in situations where you're concerned about tenants. vCluster is awesome in separating, or at least having multi-tenancy inside of your applications, but in some situations, your tenants, you want to keep even more separated, right? Like in a situation where you have like development teams that are working together, they want to share some resources, maybe some networking resources or storage. vClusters are awesome, but in other situations where you maybe have customers who are like, we want to keep things very isolated. There's vNode, which is a new product that that Loft Labs has developed recently and just released at KubeCon EU. And in that situation, that's for running a little bit more of a secure environment, and something you can definitely come out to talk to us at our booth outside. Would love to have you all join us on our Slack community. Come join the conversation as we talk about virtual clusters, and we talk about vClusters, we talk about AI running on GPUs with GPU sharing. All of those conversations are ones that I love having. Please come and talk to me. I'm there. You can find me there, I promise. If you scan that, that'll get you into our workspace. And then, if you haven't seen us, our booth's right outside. We're orange, right here. Not only are we sitting outside, we have great information for you about virtual clusters and have some hats and things. We have an author signing books right now, actually. His name's Mark Borstein. He wrote a book about the enterprise guide to Kubernetes, I believe. And he is still there. We still have a couple of free copies left. And so you please, on your way out of the room, go and visit him, and you can get a free book and visit with Mark and have him sign it for you. My name's Scott McAllister. I'm a developer advocate at Loft Labs. And thank you all for your time, and enjoy the rest of KCD.